Excellent. Okay, very good. All technical issues sorted out. Welcome back to the third session of Hope. Hope you all had a good lunch. We'll start out with a talk here by Vikraman on continuations and coexponentials. Take it away.
Okay, yep. All right, so I'll tell you some ideas about continuations and duality and how the lambda calculus can be dualized if you have native continuations. And it leads to a duality of abstraction where I think of lambda as an abstraction mechanism and lambda bar gives you a dual of lambda. So I'll start by mentioning how these ideas of duality in programming languages or computation are very common because when in the 90s, when continuations and their logical foundations were studied by various people, and Filinsky came up with the duality of values and continuations, and it led to many different ways of formalizing this through the first being Perigo's lambda mu calculus, and then it led to the mu bar calculus of Kurian and Herbelon, where there's a duality of programs and evaluation contexts. And more famously, the duality of call by value and call by name, which uses the lambda mu duality, was so Selinger had written about it, and then Wadler improved it a little bit. Okay, so these are the dualities of values and continuations in some form or the other, and Girard took these ideas of dualities and proposed classical linear logic where these dualities are very symmetric. And if you embrace classical linear logic, then there are different ways of reading A and A star or A dual as producers and consumers. Or if you think of linear logic as a logic of concurrency, then it leads to the program of session types, where Honda used them to show, to use these dual types to encode, server client and dyadic interaction. And I should mention that the latest in this, the state of the art in understanding many of these dualities is captured in the polarized adjunction models of Fiore and others, which leads to these system L calculi. So there are many of these dualities, but if you look at semantics, you realize that these are just categorical dualities, because in category theory we have arrows and arrows have duals. And it's a very deep connection between syntax and semantics that leads to these dualities. And why would you care about this? Because if you are a syntactician, you want to design languages, and these dualities give you important restrictions that you have to add to your languages and allow you to encode very fundamental facts in your language. And if you are a semanticist, then you realize that these syntactic dualities get reflected as categorical dualities in your language models. And in an ideal world, these should correspond in a very concrete sense. And if you don't think about programming languages, but also just think about duality in terms of in a philosophical sense, then if two things are dual, it means they are equally important, right? And if values and continuations are dual, then they should be equally important. And that's kind of the philosophy behind this language that I'm going to tell you about. So I prefer to start from the semantics because it helps me guide like how to design languages. So all of this is pretty much well known, like how continuations are non-returning functions from A to R, and we fix a response type R, and then we have A to R. Okay, and then different people have studied categorical semantics of continuations, and in particular, Thieleke's 1997 Edinburgh thesis on the categorical structure of CPS was based on axiomatizing the negation functor, R to the blank, which is a contravariant functor from C up to C. And the amazing thing about it is that it's self-adjoint. So it's self-adjoint, so it's adjoint to itself. And you have this very nice picture, C up to C, where you're taking negation once and twice, and if you compose both, you get double negation, which gives you the continuation monad on C. And this fact is very basic because it's just about products and exponentials. And essentially, this is what explains many things about continuations. So I'm going to exploit this kind of stuff and show you a little bit more, which is, so rather than taking this picture, I want to understand the negation functor a little bit more. So just to remind you, if you don't know about it, is that functors map objects to objects and morphisms to morphisms, but you can split functors into two, where you first only map the morphisms. So FBO here is going from C to CF, and FF, which goes from CF to D. So F going from C to D gets split into two. So this is the full image factorization, and up to isomorphism, this has a universal property. Now, I want to look at the negation functor and apply this factorization, which means I'm splitting up negation on the types, the objects, and on the morphisms. So essentially, when you do this, if you split the lower negation functor, you get CR. And if you split the upper negation functor, you get CR op. And this picture completely explains the duality of call by name and call by value. It's like a very, like a two-line explanation of why these dualities exist. And I want to mention that like these categories of negations were like very popular and studied very well in the 90s by starting from Lafont's categories of negated domains to categories of continuations by many authors. It's very unfortunate that many of these papers don't exist anymore, and there's no way to get them. And I've emailed people, and yeah, and yeah. So this call by name and call by value duality is just a formal duality here. And Peter Sullinger has written, his seminal article on control categories, and this is a very crisp picture of what's going on with control and co-control categories. Okay. So I'm going to take this semantics and only restrict to call by value. And when you have call by value, you play this same game, and you end up with a picture like this with a bunch of adjunctions and some functors explaining various properties of continuations. But let me just point out what the fundamental facts are. So it's so R to the blank is your double negation monad on C, and it's strong. And CR is the category of continuations, which is dual to the Kleisli category of this continuation monad. And this category of continuations being in fully faithful with C, it inherits a lot of structure from C. And so this is all in the abstract, and it's a I want to just mention why the name Loch Ness semantics, because it's a remark from Girard's The Blind Spot, where he has a criticism of various approaches to understanding dualities and the many mistakes that people make. But here's a way to fix many of these problems. And I want to, instead of doing it in the abstract, let me just concretely give you what all the structure is. So I'll start from a Cartesian closed category C, which means products have right adjoints, and these give you functions. So if you have a program from C times A to B, you can curry it and go from C to a function A to B. And if you take the Kleisli category of the continuation monad on C, so I fix a result type R, and then you get this coexponential adjunction, which means if you started with sums, then A plus blank is a coproduct functor, and it has a left adjoint, and this is the coexponential. So how do you compute it? Well, so C left A comma B is so the coexponential is defined to be C times R to the A, and since it's in the Kleisli category, it's R to the B, and then you just split the so you uncurry and move the continuation R to the B on the left. Now you have two continuations for A and B. You can join them to give a continuation for A plus B, and then move it back right to put it back in the Kleisli category. Okay, and then the third thing is that this Cartesian closed category C and the co-Cartesian closed category C R to the blank are in Kleisli adjunction. So C includes into the Kleisli category, and this has a right adjoint. Okay, so now this is all semantics, and I'm going to use this to produce a programming language. So the main idea is to take Moji's call by value programming language lambda v and add coexponentials. So so the first thing is that we have a distinction of values and computations, and because the continuation monad is strong, you can lift functions from the value category to the computation category, and this gives you call by value functions. And the second thing we are adding is the coexponentials. So when I say gamma, so I'm thinking of the things on the left as my contexts, and when I say gamma coexponential A, that means gamma with a continuation for A. Okay, and then the coexponential adjunction gives you this isomorphism, which is saying that if you have a continuation for A in the context, you can move it to the right and get A plus B. Okay, so this is the main semantic duality, and I want to explain the programming language view, but I'm going to do it different from previous attempts at making languages for dual languages for continuations, because they always end up in some kind of sequent calculus or some other compromises. But I want to maintain the type theorist natural deduction tradition, which is so I'm borrowing some terminology from Paul Livy, which is this idea of having types are either leftist or rightist. Okay, so when you have functions, they're always rightist because natural deduction forces you to introduce them on the right, and this lambda rule is always reversible. So you apply and you go back up the lambda. Okay, and these are inverse up to beta eta, but well, if you restrict to values, it's only up to values. Okay, and products are so products have a special thing because contexts are products of things. So if you use first and second, then products are rightist because they're always on the right. But if you use let or pattern matching, then they become leftist. Okay, so we don't have both at the same time. We pick either rightist products or leftist products. Okay, and if you think about sums are always leftist. So so sums have case and in left and in right, and you can only eliminate sums from the left. So you have a sum on the left and you case it and get out, and if you want to invert this rule, you use in left and in right and use substitution. So sums are leftist, but when I add duals, these sums now become rightist. Okay, so the dual rules I'm going to add are a lambda bar, which looks just like lambda, but the variables have a type a bar, which is a type of co-values. And if you use lambda bar to bind a co-value, you get a plus b, which is very surprising, but let me explain how that works. And just like application, there is a co-application, so I'm using @ just to distinguish it. So when you have a plus b, in the presence of an a bar, you can cancel out the a and get a b. And now sums have both leftist and rightist features, and now these are going to interact, and this is going to produce control effects. So just to give you the proper rules, it's completely symmetric, where lambdas give you functions, and lambda bar gives you sums. Okay, and application happens the other way. Okay, so even though I'm saying that a plus b is the binding for lambda, lambda bar, there is a derived dual type it's like b minus a, which is b times a bar, or you can think of it as b with the left arrow to a. Okay, and these subtractive types act completely dual to function types. So function types have curry, and subtractive types have co-curry. And so the product on the left becomes a function on the right, and a subtraction on the left becomes a sum on the right. And you can implement them using lambda and lambda bar. Okay, and this so there is a folklore belief that you can never make a programming language which has both currying and co-currying, but here's lambda bar, which has both. And these subtractive types have so there's an algebra of functions and there's an algebra of subtraction, which is functions have eval and subtractive types have co-eval, and functions have composition, and subtraction has co-composition. And so it's instructive to write these programs, but I just wanted to show them. And so this is a language for continuations, and continuations have various metaphysical interpretations and things like time travel and other things. So I'm just going to give you a simple example, which is like compare these sums, which are so when you want to produce a sum, you either go left or right, and you make a choice, right? So it's a bold choice. When I know how to prove b, so I'm going to go right and produce a plus b. But when you use lambda bar, you don't know how to prove a b. But in the weekend context, where you have an a bar, you can produce a b. And that's when you use the lambda bar. And so this is an example of a cowardly choice, which Bob Harper calls it's a pusillanimous choice. And this lambda bar, this variable x, which is my covariable, this is the location where you made this cowardly choice. And now the point is, how do you use x to do anything interesting in the body of the lambda bar? Okay, so here are some interesting programs. Of course, so the first program anyone tries to write with continuations is excluded middle, and if you want to write excluded middle, that's just lambda bar a dot a. I'm writing a bar just to show you, like it's just a normal variable, but has a dual type. And then the next thing is you can use lambda bar to derive the usual call CC. So call CC is a bar to a and produces an a. But I'm going to argue that call CC is not the right primitive. The right primitive is lambda bar, because you derive call CC by first using a lambda bar to go from a bar to a, to a plus a. And when you have an a plus a, you can get out an a by observing both sides of the choice. So there are so qual-CC is very mysterious, and different equations exist. And one of the main observations that Filinsky had made was this collapsing nature of qual-CC, and this fact, like that the qual-CC is implemented by first doing a lambda bar and then collapsing both sides of the sum is what explains this collapsing nature of qual-CC. And so lambda bar is a generalized qual-CC, and co-application is the lambda bar application, and it's how you get a generalized throwing mechanism. So with co-application, you make the in left and in right interact. So now I have a throw which takes a value and a co-value, and I can lift the value to the left and co-apply the co-value, and this acts like a throw. So from A and A bar, you get a B. And similarly, you could derive abort by using 1 bar for 0, and it's the same thing. Okay. So essentially, this language is a complete language for continuations. You can implement various things, and you can show that if you so there's a Curry-Howard with Gensen's SLK, which is the classical logic sequence calculus. So if you can type some term in lambda bar, it's a formula in classical logic. It's a derivable formula in classical logic. Okay, so now these are interesting programs, but how do they actually run? So I have a few minutes, so let me show you some. So first, like it's lambda. Lambda has beta eta equations. Similarly, lambda bar has beta eta equations, and there's a theory of substitution as well. And the control effects are so these control effects are. So I'll tell you some equations. So for example, if I'm using lambda bar, and I already know I have a b and never actually use my x, it's the same as doing a deterministic choice. If I apply things on the right, they just get passed around. So E is an evaluation context, and it gets preserved when you collapse the lambda bar and the right. Okay. If it's an in left, then an actual control effect happens, because here's an E on the left, which gets discarded. And this is a jumping effect, which discards your evaluation context. Okay, so you can write programs, and some programs that you write with qual-CC, you can also write them using lambda bar. But I wanted to show that how these are like exceptions. So there's this fast multiplication example where you're multiplying elements in a list, but if you see a 0, you don't want to continue the multiplication, so you want to short circuit. And you add a clause like this, loop 0, so which tests if the head is 0, and then if you multiply 1, 2, 0, 3, 4, it goes 1 times 2 times 0, but then still performs vacuous multiplications. Okay. So now let's think of rewriting this using sums. Okay, so I have a list and I want to return int plus int, where the left-hand side is going to be the exceptional value, which is 0, and the right-hand side is the actual multiplication. So you write it where when it's empty list, it's in right 1. If you see a 0, it's in left, and keep mapping on the right. But I'm also adding a side effect here to observe what's being what part of the list is being traversed. So this doesn't perform any vacuous multiplication, but it's still going to traverse the list, and it's going to print at 2 at 1. Okay. Now you can do even better, which is using lambda bar. You return int plus int, but you use a lambda bar to generate a backtracking point. Okay, and then you have the same thing. The same program, but when you see a 0, you use the lambda bar bound x to throw something on the left, and then the rest of the program is the same. And this will not perform any multiplication with 0, and it will also not print any trace. So here's the program where like actually these sums are useful, So there are 2 more equations for lambda bar, which describe the speculative nature of these sums, which is like when you case on a speculative sum, it's going to it's going to speculatively evaluate the right-hand side. Okay, so I'll show an example. So let's say I took the law of excluded middle and tried to observe it. So it's either so if it's on the left, I print 0. If I return a 1 on the right, and if you apply these reduction rules, this whole thing collapses and it's going to go on the right. So you observe the excluded middle, but it prints 1. Okay, but you can write this other program which uses the right-hand side continuation to throw, and you would think that it should return 1, but a bunch of things happen with these equations, and it actually changes its mind at the last minute and returns 0. So this is how the operational semantics of excluded middle works. Yeah, so these equations I've given you, these are a complete axiomatization of control effects, and you can derive all the Indiana control operators and their equations, or you can derive the Hoffman equations from these, and so these axiomatized control. You can do a bunch of other things with this language. It's a good language to understand backtracking, and you can encode effect handlers by doing a CPS transform of the free monad. I have things on GitHub if you want to check them out, and I'm happy to talk about them. There are other applications of this duality. So it can dualize functional completeness. So you might know this as the environment comonad and the reader monad, but if you CPS and then dualize functional completeness, you get an exception monad and a handler comonad. Okay, and this can be used to dualize arrow languages. Okay, these ideas are related things that many other people have built, and it essentially is about how you axiomatize continuations, and there are different ways of doing it. I mentioned them for completeness, and there are other examples of this kind of coexponential. You can do them in linear logic and with other continuation monads, and in fact, there's a way to read all of this in quantum theory using effect algebras and other things. But I'm happy to discuss other ideas if you want to. Anyway, so to conclude, I'll just mention that there's this duality between functions and continuations. Functions give you exponentials, and continuations give you coexponentials. And there's a language where this is made very explicit, which is a good language with semantics and implementation in ML and Haskell. And you can see more on my website. There's a draft and other materials and things. Yeah.
All right, let's thank the speaker. We do have time for a couple of quick questions. Question down here.
Sure. Can you? So you mentioned how often you said it was a folklore result that that coexponentials sort of always lead to collapse. Of course, often it's not folklore, right? But if you just have a category that just sort of has the exponentials and the coexponentials,
right,
it does fall apart. So I didn't quite grasp, you clearly don't run into that problem. So can you explain how you avoid that?
So mathematically, there's nothing going on. I'm actually splitting them into two different categories, but they're connected by a Kleisli adjunction, and so you can put them in the same programming language, but just add a value restriction. Yeah.
All right. One more question.
Yeah.
So whenever I see someone use call by value in their semantics, I wonder what would it look like in call by push value? Because you have a category of algebras and a category of values here.
Yeah, sure. Yeah, so if you did that, so I can show you in fine-grained call by value. So you'd have intuitionistic sums in values and classical sums in the computation. So it'll actually split. So then there's no interaction unless you have a force and thunk going between values and computations. Yeah. So. Yeah.
All right, thank you. I think you have to take the rest of the questions offline.
Yeah, and I'm happy to talk about it offline.
Yes, let's thank the speaker again.